and that gives you the equation of motion, that gives you the condition dds dx mu ds times minus eta rho sigma x dot rho x dot sigma equal to the minus half is equal to 0. Now you can show that this object is nothing but dx mu d tau. Show. So dds dx mu d tau is equal to 0, or d tau ds d2x mu d2x mu d tau 2 equal to 0. This implies that either d tau ds equal to 0, which is the massless case, or d2x mu d tau 2 equal to 0, which is the massive case. Okay. Now next, so far so good. We have an action, relativistic action, and we seem to have a satisfactory situation so far. However, there is one problem. The problem is that when we do path integral calculation, we have something to integrate this e to the power I by h bar s prime, and that has s prime has a square root form, and that integration is not very easy. And if you could look at it in a different way, that if you have a square root action or Lagrangian, then quantization will be more difficult. So question is that s prime of x has a square root form as a square root form. This can pose difficulty in performing path integral using this action. Now, given the classical equations of motion, corresponding action is not fixed. You can have multiple action. Multiple action can produce same set of classical equations of motion. Question is, although this action S prime is a geometric, is it possible to construct a quadratic action which will reproduce the same equation of motion? So question, is it possible to come up with a quadratic action which produces same equations of motion? Because we know that quadratic actions are easier to handle because their path integral is Gaussian. We have already done this calculation for a free particle harmonic oscillator. So answer is yes, and Answer is yes. The action that does this job has this form ds lambda is inverse eta mu nu dx mu ds minus mu square lambda is. So this lambda is a new field over which path integral needs to be performed. However, this is an algebraic, this is a non-dynamical field. However, a non-dynamical field as Sx, as there is no time derivative, as lambda is doesn't appear with time derivative. This type of actions, this type of fields produce constraints. This type of field produce constraints because their equation of motion is not they produce constraints through their equations of motion. So so for a lambda a's equation of motion is delta s over delta lambda s equal to 0 gives you an algebraic constraint where lambda s must be given by minus 1 over nu square x dot square to the power half, where I'm using the x dot square as a shorthand for d mu nu x dot nu x dot nu. So when you extremize the action with respect to lambda and calculate that extremum of extremized action, then you should get back to the original action, because lambda, our goal was to find an action which has the same classical content of the original action. The original action did not have lambda. New action has a lambda. This would mean that when lambda is extremized, then it gives you the same action as we had earlier. Okay, if that is satisfied, then it is acceptable. Okay, so it is indeed the case, lambda extremized action is given by s is equal to integral ds lambda inverse, which is nu divided by square root minus x dot square times x dot square minus lambda, which is 1 over nu minus x dot square nu square. And that's okay, I could take a half outside, and then that would give a half outside, and that would be minus mu integral ds square root of minus x dot square. Yeah, that is s prime. So lambda extremized S is same as S prime, so which means that S will give you the same equations of motion for as required, as desired, as S prime does. Okay. So now there's one subtlety here, which is extremely important when we do the path integral calculation. The subtlety is that original action, since S is an unphysical parameter, I probably should have emphasized it before. Since S is an unphysical parameter, here we mentioned that this is an internal parametrization, and hence this is unphysical, and that would mean that these action, to begin with, that would mean that these actions should be invariant under reparametrization of S, because if I instead of using S as a parameter, if I use another parameter, say S prime, which is basically secretly I have done here, right? I have done the reparametrization from tau to an S with this type of properties, but from this S I could go to another S prime and describe this in terms of S prime. Physically, nothing would change. No physical content should not change, because it's a non-physical parameter, and that is actually true for this action, which I forgot to mention before. This is indeed S reparametrization invariant. If you do a reparametrization, S going to S prime, then there's Jacobian, which is ds prime ds. It will be quadratic in here, and it will be inverse of that here coming from the measure, and they will cancel. Okay, and so under S going to S prime, this action is invariant. So when I replace S prime by this quadratic action, I better maintain the same S reparametrization invariance for the action, and that would require lambda of S to transform under S reparametrization in a particular manner. Okay, so let me discuss elaborately the here for both S prime and S, the S reparametrization. So invariance under S reparametry. Invariance under S reparametrization. So geometrically, what happens is that this is your path given by x of S, which means at a particular value of S, there is a. So this x path is actually a map from the line segment to the Minkowski space, four-dimensional Minkowski space. It's a real line segment, 0 to 1. S varies from 0 to 1, and an even value between 0 and 1. Correspondingly, you have a point in the space time. Right now, if you change S to say S tilde, then it is the same point in Minkowski space that is now corresponds to S of tilde. So if you change the parametrization, we should the field, so x of S can be viewed as a one-dimensional field. So this is one-dimensional field. This one-dimensional field or a function, the functional form must change. So x of S must go to x tilde of s tilde such that it is same as x of s. So this x of s is a function which determines what point in the Minkowski space that particular point on the trajectory parameterized by s corresponds to. Now, if you change that parameterization, then this form of the function changes. So how does it happen? Now, this form of the parameterization is same as x of s, which means you take x of s and replace s by its functional form in terms of s tilde. So this is a function of a function, and therefore that is called another function, which is x tilde. So such a field which transforms in this way is called a scalar field. So it happens for each value of mu. Though x mu is a coordinate in Minkowski space and therefore is a vector in under Lorentz transformation. However, as a viewed as a one-dimensional field dependent on the parameter s, it's a scalar field. So invariance for so therefore s prime of x goes to s prime of x tilde, which is minus nu integral ds tilde minus eta mu nu dx tilde mu ds tilde dx tilde nu ds tilde to the power half. And as I was mentioning, it is same as ds times ds tilde over ds, and this is minus eta mu mu dx tilde mu is same as dx x of s dx mu ds, but at the same time ds tilde, this is the Jacobian factor you get, whole square. So when you bring this out of the square root, it becomes ds tilde, which cancels this, and it becomes same as s prime of x. So this is the invariance, reparameterization invariance of the original action. Now, what would be the reparameterization invariant of the quadratic action? So this is square root action. Now let's look at the quadratic. Quadratic action is tilde of x tilde and lambda tilde. S tilde is not only a function s of x, so I should change this notation. It is s of x and lambda. And this will be given by ds tilde lambda tilde inverse x tilde dot square minus lambda tilde mu square. And it is easy to show that this is same as integral ds f dot lambda tilde f dot lambda tilde inverse x dot square minus f dot lambda tilde just a moment. Yeah, f dot lambda tilde times new square, where f is this function of s and f dot of s is df ds. So you demand the same as to be same as this. This is you demanding. And that tells you that you should have lambda tilde of s tilde. The transformation of lambda should be 1 over f dot s times lambda s. So we should demand lambda to transform in this fashion, and if that happens, then this quadratic action is reparametrization invariant too. So we will proceed to calculate the path integral in the next time, in the next video. Okay.